In this video, I want to talk about surfaces in three-dimensional space. Based on things we've done before, we already know about a couple of surfaces, so let's remind ourselves of that. Shortly after we figured out how to calculate distances in three-dimensional space, we figured out that the equation of the surface of a sphere of radius r and center ABC is given by this kind of equation. An equation that looks like a constant times x plus a constant times y plus a constant times z equals a constant, we figured out that that represents a plane at right angles to the vector with components a, b, and c. Generally speaking, if I have an equation that looks like some expression that may involve x, y, and z equals another expression that may involve x, y, and z, by may involve, I include the case of one of the things being a constant. This is going to represent some sort of surface in three-dimensional space, such as a sphere or a plane or some other type of surface. In this video, we're going to look at three types of surfaces, namely the cylindrical surfaces, surfaces of revolution, and the quadric surfaces. What we're going to call cylindrical surfaces are created in this way. Imagine that you have a curve that lies in a plane, this curve for instance, and you have a straight line that is not contained within that plane. It cuts through it at some angle or the other. Take each point on the curve and draw a straight line through it that is parallel to the given straight line. If you look at all possible such straight lines, which are sometimes called the rulings of the surface, you get a sort of cylinder-like surface whose cross-section is the curve that you started with in the plane. The reason that we call these things cylindrical surface is, for example, this one looks a little bit like a cylinder, but I can draw one that looks even more so. If the plane is the xy plane, I can draw a circle in the plane. I'm going to think of the circle x squared plus y squared equals 1. The straight line not in that plane is going to be the z-axis. So for each one of those points, I'm going to draw a straight line through the point that's at right angles to the plane, is parallel to the z-axis. If I only draw in a few, you begin to see what's happening. Every point on this circle is going to have one of these lines through it, and as a result, I get a continuous, unbroken surface when I look at all of them. The issue of how to write an equation for such a thing is not as complicated as you would think. In fact, it's simpler than you'd think. If I'm in the xy plane, the points on the circle are exactly the x's and y's that obey x squared plus y squared equals 1. If I take any one of those points and alter its z-coordinate from being 0 to being not 0, I'll trace out one of these straight lines. In three-dimensional space, the equation for this surface is just going to be x squared plus y squared equal 1. As long as the x and y coordinates obey that equation, the z can be taken to be whatever value you care to make it. As a result, we're going to have to be very careful about the context. If I say that equation is true, depending on the context, I may be talking about the circle in the two-dimensional plane, or I may be talking about the cylinder in three-dimensional space. If I'm talking about surfaces, and I make the plane that contains the curve one of the coordinate planes, all that goes on is you have an equation that relates two of the coordinates, but not the third. Sometimes people find that to be very disturbing. If it makes you feel any better, you could write something like this. You could write x squared plus y squared plus 0 times z is 1. It doesn't make me feel much better because it makes the equation more complicated. It's going to be up to us to keep this straight. As another example, let's think of the graph of the equation z equal y squared. If I'm working only in the two-dimensional yz plane, this is just a parabola. If I'm working in three-dimensional space, though, if I'm working in three-dimensional space, though, I should regard this equation as being something that relates x, y, and z. It's just that x doesn't make an explicit appearance. So any two numbers y and z that look like that can be assigned any x you care to, and we will have a point on our surface in three-dimensional space. In a feeble effort at drawing a picture of this, I've drawn this dotted outline, which is supposed to be a piece of the YZ plane. I've drawn another one at some fixed x value and is parallel to the YZ plane. I can think of taking the graph of z equal y squared in the YZ plane and just sliding it out until every point has had its x coordinate changed by the same amount. This will also be part of my graph. Every parabola in between those, and every parabola that you could get by extending this in either direction, will also be part of the surface. The shape I'm going to get is as though I took a piece of paper and curved it in the shape of a parabola this way. So as you can see, this graph is just a parabola that has been slid sideways parallel to the x-axis. A second type of graph that I want to think about is surfaces that are obtained in this way. I'm going to start in some two-dimensional plane, for example the xy plane. I'm going to have the graph of some function of one of the variables in terms of the other one. Here, y is going to be a function of x, meaning that if I give you a certain x value, I can tell you how far out from the x-axis is by looking at f of x. If f of x is positive, that tells me the literal distance here. If f of x is negative, I'm looking at the negative of the distance. Since we're going to end up squaring, it doesn't make any difference. If I imagine in three-dimensional space having that same situation, I can grab the x-axis and use it like a knob to spin the entire picture around the x-axis. This individual point is going to go around in a circle that is in a plane parallel to the YZ plane. The equation of that circle is going to be y squared plus z squared equals the radius squared, with the understanding that the x-coordinate is being held fixed. If you do this for each one of these points on this graph, you get the following equation. It's worth mentioning that the structure that I'm thinking about has to be right. Y squared plus z squared is the square of f of x. Y and z are two of my coordinates, and what shows up over on the other side does not involve y and z. It can only involve the other coordinate. Otherwise, if there were y's and z's over here, whatever it is I'm looking at might not even be a circle, and even if it was, the center might not be on the x-axis. So this is a pattern. A variable squared plus another variable squared equals something that can depend only on the third variable. So, for example, in the xy plane, think of the graph of y equals x squared. I'm going to revolve this around the x-axis. The distance from the axis of rotation to the point on the curve is literally the y-coordinate, but y is equal to x squared here. This point is going to go around in a circle parallel to the yz plane. On one side of this equation is going to be y squared plus z squared, and over on the other side, I have to write down the square of the radius of the circle, making sure to express it so that there's no y or z in it. The resulting equation, y squared plus z squared equal x to the fourth, represents a sort of horn-shaped surface. Likewise, I'm going to take the graph of y equal x in the xy plane and revolve it around the x-axis. On this side, x is positive, so this distance is literally equal to x. Here, x is negative, y is negative. This y-coordinate, x, is not the distance, it's the negative of the distance. Since we're going to square the radius anyway, we'll have an x squared and get the correct radius squared, regardless of whether x is positive or negative itself. I think it's pretty clear that the surface that I'm going to get by taking this part and revolving it around the x-axis is this half of a cone, and when I revolve this part around the x-axis, I get that part of a cone. I get a double cone with circular cross-sections. Each of those circular cross-sections is going to be parallel to the YZ plane. To try to keep the picture comprehensible, I've drawn in only half of the line y equal x in this darkened bit. Pick a point on that line. Its distance from the axis of rotation, the x-axis in this case, will be described by either x or negative x. This point goes around in a circle parallel to the YZ plane, so I can just write down the equation for this. The radius is either x or the negative of x, depending on the sign. Square that and you get x squared either way. The equation for this double cone is going to be y squared plus z squared equals x squared, and the axis of symmetry of it is going to be the x-axis. As a second example, I'm going to look at x squared plus y squared equals z squared minus 1. This has an interesting feature. If z squared were smaller than 1, this would say that x squared plus y squared would have to be negative, which can't happen. So we have no points for a certain range of z values. The first z value that's positive, that's actually going to give you a point, would be z equal 1. That would mean that x squared plus y squared is 0, which would mean you're talking about the origin only. The same thing happens if z equals negative 1. For z values that are between 1 and negative 1, though, we get no points at all. On the other hand, if z were 2 or negative 2, this would read x squared plus y squared equals 3, which are circles in planes parallel to the xy plane. Obviously, just like in other situations, the further away from the xy plane you get, the bigger the circles will get. And to determine the shape of the thing, all I've got to do is look at cross sections with the other coordinate planes. If y is 0, then x squared is z squared minus 1, and after rearranging a little bit, z squared minus x squared is 1. This is a hyperbola which will have z-intercepts at 1 and negative 1. If x is 0, then y squared is z squared minus 1. This is the same as this, except the letter x has been replaced with y, so the result will be the same. The cross sections in the other two coordinate planes are hyperbolas. So we get a figure that is separated into two separate chunks, the upper chunk and the lower chunk. One of the set of cross sections are circles, and the others are hyperbolas. We call such a thing a hyperboloid of two sheets because it's in two pieces. This equation looks a great deal like the equation of the parabolic bowl, except it has a minus instead of a plus. This turns out to be the most complicated of the commonly seen shapes that we'll look at. For a reason that I'll tell you in a little while, I'm going to avoid looking at z equals 0 for a moment, and I'm only going to look firstly at a cross-section in a plane parallel to the xy plane above it, and also below it. If z only takes on value 1, my equation becomes 1 equals x squared minus y squared, which is a hyperbola. It opens sideways. If z is negative 1, then negative 1 is x squared minus y squared. I'll multiply both sides by negative 1 to put it into the more convenient form for a hyperbola. Y squared minus x squared would be 1. I get a hyperbola again, but weirdly, this one opens in the up and down direction instead of the sideways direction. So if I intersect my surface with a plane of positive constant z coordinate, I'll get something that looks like that, but down below the xy plane, I get that kind of thing that's been reorientated. It's been turned 90 degrees. Next, I'll look at what this looks like if I intersect it with the plane where y is 0. That would be the xz plane. And also, what happens if x is 0? That would be the part of the surface that's in the yz plane. If y is 0, then z equals x squared. This is an upward opening parabola. If y were some number other than 0, I would have z equals x squared minus a positive number, it would look just like this, except it would be lowered down. If x is 0, then z is the negative of y squared, which is a downward opening parabola. If x were something other than 0, x squared would be positive, and this would be lifted upwards in the z direction. So, summarizing our conclusions, if I'm in a plane parallel to the xy plane but above it, the intersection looks like that. If I'm below, it looks like that. If I hold the y value equal to a constant, then in a plane parallel to the xz plane, my graph looks like this, while if x is constant, then the graph in a plane parallel to the yz plane looks like this instead. On the face of it, it seems almost impossible that there would be a shape like this. I've learned that if I try to draw this with the coordinate axes in the picture, it becomes almost illegible. So I'm just going to draw this by itself. This is the x direction, this is the y direction, and z is vertical. In one direction, the surface looks like upward opening parabolas. In another, it looks like downward opening parabolas. If I'm up above the xy plane, the intersection will consist of two pieces, one of which opens this way, the other one of which opens that way. And if I'm down below the xy plane, I get my two pieces of hyperbola again, except this time they open in a direction that's at right angles to the way the other ones were opening. People often call this a saddle surface for obvious reasons. It's also known as the hyperbolic paraboloid. This is the most complicated of all of the shapes we've looked at. This has just been a quick description of some of the common surfaces that we can encounter during the rest of our work. I hope everybody is having a good day, and I'll talk to you again soon.